Okay, in this video we are looking at inducing a potential difference and a current. Okay, so we know if we take a current carrying conductor and place it perpendicular to a magnetic field, then the wire will feel a force on it. And that is because the field surrounding my wire, due to my current, is interacting with the permanent magnetic field for my magnet. Okay, don't worry, if you're unsure about all of that, just make sure that you watch the previous videos before returning to this one. For those of you who were happily nodding along, let's continue. So, this effect actually works in reverse. I know. Now, try to control your excitement long enough for me to explain. You can take a wire, you can put a force on it, like pull it through a magnetic field, and you will get an induced potential difference. Remember, for GCSE, that's very similar to just saying voltage, across your wire. Yep, that's right. You've taken a conductor, you've pulled it through a magnetic field, and somehow you will get a reading on your voltmeter. And if that wire then happens to be part of a complete circuit, you will get a current running through your wire. Don't believe me? Let's see this effect in action using a straight piece of wire first.
So here is a very big and very sensitive ammeter. So it is going to measure any current that flows through my wire. Currently, I have just got a piece of wire here. It's not connected to a supply. There's no current running through it, but it is completing a complete circuit with my ammeter. Here is my permanent magnet with my two poles here and here. And what I'm going to do is I'm going to drag my straight piece of wire straight through those two poles, and it is going to cut those field lines that exist between those two poles as I do it. Like so. And you will see that tiny little deflection, which is actually showing that current, which is now running through my wire.
Okay, so pretty cool. And you don't just have to move the conductor through the magnetic field, you could move the magnetic field through the conductor, Let me show you an example of moving a bar magnet through a coiled piece of wire or a solenoid.
Okay, here I have my big, very sensitive ammeter, and right now it's completing a circuit with my big coil of wire here, but at the minute there is no current running through this circuit. I am going to take my bar magnet and I am going to move my magnet relative to this coil of wire and see if I can get a current in my circuit. So if I push my north pole in, I get that slight deflection off to the right, and if I pull it back out, I get my slight deflection off to my left. If I swap my pole around, when I push my south pole in, I get a little deflection off to the left, and when I pull it out, I get a little deflection off to the right. Okay, and that current came from the fact that I was moving my magnetic field relative to my conductor. My conductor, or my coil, was cutting all those magnetic field lines as my magnet moved through the conductor. Okay, right, so obviously that was a bit lame, so let's try it with a stronger magnet. When I push my magnet in this time, get a much bigger deflection, and when I pull my magnet out this time, oh yeah, bigger deflection again.
So since you can move either your conductor or your magnetic field, we just talk about them moving relative to one another. And the reason is because when we move, let's say, our magnet into our solenoid coil, that coil is cutting the magnetic field lines of that magnet. Similarly, when I move my straight wire down in between the poles of my magnet, that wire is cutting all those magnetic field lines between the poles. So now we need to consider, how can I affect the size of this and the strength of this current that I am inducing? And let's talk about size first. So first thing you can do, you can increase the strength of the magnet. You can also move your wire through the magnetic field faster, or if you add more turns to your coil, this will also increase the current. And what about the direction of the induced current? Well, let's take our bar magnet and our solenoid. You can change the direction that you're moving your magnet So I can move it into the coil, or I can move it out of the coil, or I can reverse the poles. So instead of moving my north pole in first, I can move my south pole in first. And it is this effect that generates electricity in power stations for the UK. So it's a pretty big deal. Now, you need to know something about the direction of the current that you induce. You've moved a wire through a magnetic field and you got a current. Congratulations. Now, we know that now because you have a current in your conductor, that has its own magnetic field associated with it. And that magnetic field is in a direction such that it opposes the motion of that conductor. So, for example, when you move your bar magnet towards your solenoid and you induce a current in your solenoid, the magnetic field associated with that current tries to repel that bar magnet, making it more difficult to push it into the coil. For your GCSE, you simply have to say the induced current opposes the change that caused it. And honestly, to explore that in any more detail, it's called Lenz's law, and you need to be doing A-level physics. Okay, hope you found that useful. Please do like and subscribe. If you would like, download the notes. Thanks for watching.